So in this workshop, what I'm going to do, I want to show you how Agentic AI can move beyond what you've probably been doing in text generation and begin to work with real healthcare data and a real healthcare system. So the key idea is that the LLM that we're going to use today becomes more useful when it could reason, call tools, retrieve data, and take the next step based on evidence. FHIR gives us a standard clinical layer for doing just that. And over the next 2 hours, I'm going to move between concepts and working examples so you could see both the architecture and practical implementation. Before we begin, I'm going to give you a quick note on early access programs. InterSystems is running a number of these. If you're interested, check around the conference because there's EAPs and AI, interoperability, and developer tooling. You might be interested and you could sign up for these and you could get access to really cutting-edge technology early in its evolution. And on a practical note, please use this Ready event app to leave feedback on the session. Now, workshops like this become even more useful when we know what landed well, what was unclear, and what you want more to see next time. And there will be a next time. So this feedback helps us refine both the content and the tooling around it. I'm breaking this workshop up into 2 halves. The first half of the workshop builds this conceptual foundation we need. We're going to start with why Agentic AI and FHIR fit together, then clarify the difference between an LLM, a workflow, and an agent. From there, we'll talk about why FHIR becomes such a useful knowledge layer and why terminology normalization is often the hardest part of the entire system. I will close the first half by previewing this architecture for the FHIR summarizer so you have a clear mental model before we move into the demos. In the second half, we're going to shift from architecture to execution. I'm going to walk you through tools that this agent uses against a real FHIR repository, an Iris for Health FHIR repository in the Iris Community Edition. We're going to look at retrieval patterns such as direct reads, searches, patient compartment retrieval, and then show how large FHIR bundle can become transformed into a compact clinical summary. And then we'll end with some remarks on safety, design patterns, and production concerns, because a convincing demo is not the same thing as a deployable system. Now, everything today I'm showing you is reproducible. There is an open repository for this agent framework. I still have flash drives up here. If people want to install this onto their own system, there's some development instructions that we could give you. It's easy to run, but I'm going to demo all of this, so you don't need to do this now. You could do this after the conference is over. But I want you to know that all of this is open source. None of it is closed. You could get access to it, play with it to your heart's content, modify it to your heart's content. Sometimes people have problems with installing our FHIR server system or setting it up. And I've created some videos that you could watch in our developer community, and I believe they're on YouTube, to set up a FHIR server. And so that's all you really need in addition to the agent's software to get going. But after the conference, you'll also need a OpenAI key. We're using a low-cost GPT 4.1 mini model, but there would be a small amount of cost in using it with doing these demos. So let me start off with the problem we're trying to solve. Before we talk about specific tools, we need to understand why healthcare is such a compelling use case for agentic systems and why FHIR is especially a strong fit for agentic AI constituting its data layer. Healthcare data is highly structured, but that does not make it easy to use. It is longitudinal, spread across systems, full of relationships between resources, and saturated with terminology. A patient record is not one document and not one table. It is a graph of clinical facts accumulated over time. This is why interoperability alone is not enough. FHIR helps standardize access to the data, but someone or something still has to interpret what matters in context. Now, LLMs are excellent at language tasks. Based on their own, though, they're not enough for healthcare workflows. They do not query FHIR servers by themselves. They do not safely traverse complex clinical relationships, and they do not reliably maintain structured context across hundreds of resources. Most importantly, they do not inherently know when an action is too risky to automate. So the lesson is simple. LLM models are powerful, but the system around the LLM model is what makes it useful in healthcare. Agentic AI changes the role of the model. Instead of being the entire application, the model becomes the reasoning engine inside a larger system. It can help plan, choose tools, retrieve external data, inspect results, and continue until it reaches a goal. That shift matters because healthcare work is rarely a one-step text problem. It is usually a sequence of retrieval, interpretation, validation, and sometimes action. So this is where the fit between agents and FHIR becomes clear. FHIR gives us a structured clinical data, standard APIs, and meaningful resource relationships. Agentic AI gives us reasoning, orchestration, and the ability to work across several tools in a sequence. Put together, you get a system that can translate a natural language request into structured retrieval, meaningful interpretation, and an output that's useful to a human. So FHIR is the data layer. The agent is the reasoning and execution layer. So let me broaden the discussion a bit. I want to make sure everyone is grounded in the core agent concepts before we return to FHIR-specific patterns. At a technical level, an LLM is a probabilistic model that predicts the next token. That sounds simple, but the behavior that emerges from training at scale is powerful. We're doing reasoning, summarization, transformation, and instructions following. At the same time, an LLM is stateless by default and has no built-in connection to your systems. So architecturally, it is better to think of the LLM as a reasoning primitive, not as a complete solution. A system becomes agentic when we put the model inside a control loop. The model can plan, select tools, observe results, maintain intermediate state, and decide whether another step is needed. That means we move from one-shot inference to multi-step execution. The important point is that the agent is not just the model. It is the model plus the loop, plus tools, plus constraints, plus state. It is helpful to distinguish these patterns clearly. A prompt is a single turn. So you ask a question and you get a response. A workflow is multi-step, but the path is predetermined by the developer. An agent is different because the model can decide the next step, choose the next tool, and adapt after seeing the results. That distinction matters because not every LLM application should be called an agent. In this workshop, FHIR appears as one of the tools and data sources an agent can use. When some hear the word agent, they often picture only the LLM model. In practice, an enterprise agent is a coordinated system. It starts with a user request, which becomes the goal. The model or planner decides what to do next. Tools and connectors provide access to the outside world. State and memory keep track of progress. Policy and approval layers govern higher risk actions. And logs, evaluation, and monitoring make the system observable. In healthcare, those non-model pieces are what turns a clever demo into an enterprise system. A good rule is start simple and add autonomy only when it genuinely helps. Agent behavior is most useful when the task may take several steps. The path is not fully known in advance. More than one tool may be needed, and new information can change the next decision. If the task is just one lookup or one deterministic business rule, a simpler workflow is usually the better design. This diagram shows the enterprise loop more explicitly. A request comes in, the model forms a plan, the tools return evidence from the environment, and the agent continues until it reaches an exit condition. Around that loop sits the guardrails, validation, approvals, logging, and evaluation. The key point is that this architecture is not specific to FHIR. It rather is the knowledge layer inside a more general agent pattern. Autonomy is rarely all or nothing. Most real systems use graduated autonomy. The agent may read and summarize safely, recommend a next step, or draft an action for review. But when the action can change clinical data or affect care operations, policy checks and human approval become essential. That is not because healthcare is uniquely anti-automation. It's because higher consequent actions deserve stronger control and better auditability. A realistic agent architecture assumes failure will happen. The question is whether the failure is safe and visible. Agents may choose the wrong tool, work from incomplete data, get stuck in loops, misread an ambiguous request. Oh, and I had this ambiguous request several times in the last session, or attempt something that should never have been done automatically. Each of those failure modes needs a design response, clearer tool boundaries, evidence checks, max turn controls, clarification prompts, approval gates, and logging. Good systems are engineered for recoverability, not just success. And we'll probably see that in this session too. Before we go deeper into FHIR, let me share a healthcare example that does not require any FHIR knowledge. Imagine referral intake. An incoming fax or PDF or email arrives. The system extracts the key fax, checks policies or routing rules, drafts the next step, and asks for human review when needed. It is easy to understand the pattern. Let's see how FHIR then fits into the same overall architecture as the structured clinical data layer. Here's a picture of our architecture. The point is not to memorize the diagram, but to see how the reasoning layer, the tool connection layer and the healthcare data services fit together into a coherent workflow. Agents don't do everything themselves. They rely on tools. These tools may be APIs, databases, search systems, vector indices, terminology services, or FHIR servers. The model decides, the tools execute. The separation of concerns is one of the most important design ideas in the workshop. When the tools are clear and well-bounded, the prompts become simpler and the whole system becomes more reliable. This is the core execution loop in practice. Reason, act, observe, and repeat. The agent interprets the request, chooses the next tool, executes the step, inspects the results, and decides whether another step is needed. So this is like a state machine with feedback, more like that than a chat interface. That loop is what enables iterative refinement, tool selection, and error recovery. As the system grows, one general-purpose agent tends to become brittle. Sub-agents help by narrowing scope. You could have one sub-agent for retrieval, one for terminology resolution, one for summarization, and another for workflow orchestration. That improves modularity, reusability, and testability. And we'll be seeing this actually because our system uses a sub-agent. We'll get more into the details of that in a little bit. I want to say a word about Model Context Protocol, or MCP. MCP is not an agent. MCP is a connection standard that helps an agentic application discover capabilities, request context, and invoke tools in a consistent way. Simply, it's the standard connector layer between an AI host and an external system. In healthcare, those external systems might include FHIR repositories, terminology services, search layers, policy engines, or scheduling systems. So, two common questions. Who introduced MCP and why did it need to exist? Well, Anthropic introduced it in 2024 and it became a wildly successful standard. The practical problem it addressed was the following: integration sprawl. Every host talking to every tool through a different custom connector. Well, that's expensive, brittle, very hard to maintain. MCP emerged to replace that fragmentation with a shared open protocol. The value is not just elegance, it's lower integration friction, better portability across hosts and tools. Healthcare agents rarely need only one system. A useful agent may need structured FHIR data, terminology services, approval logic, policy content, search, and enterprise workflows. MCP matters because it provides a more uniform way to connect those systems. It does not replace FHIR. It makes it easier to compose FHIR with other services that real healthcare workflows usually require. Currently, our FHIR agent uses MCP to connect to terminology-oriented services. But I would emphasize that terminology is only one use case. The larger takeaway is that MCP lets you standardize how the agent reaches external capabilities, whether that capability is code resolution, search, policy lookup, or scheduling. When people first hear about MCP, they often reduce it to tool calling, but the protocol is actually broader than that. It standardizes the overall interaction contract lifecycle, transport, resources, prompts, tools, and the way the host and server understand each other's capabilities. The broader contract is why MCP can support both local and remote patterns and why it's useful as an architectural standard rather than just a convenience feature. Well, the future trajectory of MCP suggests movement toward a broader open ecosystem. I think we're going to see in the next several years better discovery, more formal governance, and stronger production readiness patterns around trust and security. MCP appears to be the tool that's moving, or the protocol that's moving from its early stages to a more mature ecosystem. So stay tuned to this, and we'll probably have more to say about this next year. So let's now return from the general agent discussion to the healthcare data layer. Here, the idea is that FHIR becomes the structured substrate the agent can reason over. Instead of asking the model to infer structure from text, we ask it to work with well-defined FHIR resources and FHIR relationships. FHIR gives the agent a predictable and queryable interface. It provides resource types, consistent RESTful FHIR APIs, search parameters, and a standard way to retrieve and traverse clinical information. We don't have time to get into the riches of the FHIR schema and all the APIs, but for the agent, FHIR becomes a tool with a strong schema and meaningful semantics. The FHIR data layer, although complex, is more standardized than in many industries. So let's focus on the separation of responsibilities. FHIR gives structures, APIs, and terminology bindings. The agent adds natural language understanding, multi-step reasoning, and contextual interpretation. FHIR does not answer the question by itself. The agent does not manufacture the data. Each plays a distinct role, and that clean boundary is what makes the architecture maintainable. Here's an end-to-end healthcare-specific view. The user asks a question in natural language. The agent receives it, resolves terminology as needed, calls the appropriate FHIR tools, gets the results back as a bundle or a set of resources, extracts the relevant structures, and then uses the LLM to generate an answer. This is much closer to a back-end workflow than a standalone chatbot. The summarizer pipeline that I'm going to show you in a few minutes is a concrete implementation of this architecture. First, we retrieve the patient record, often with a $everything request of using the FHIR APIs. Then we parse this bundle, and we get back a search set bundle that we parse. We extract clinically relevant features. Only after that do we pass the structured context into the LLM. The key design principle is that we do not send raw FHIR to the model if we could avoid it. We transform it first, and you'll get to see this. For those that are maybe new to FHIR or not work with it extensively, FHIR is a complex directed graph. There's over 150 atomic units called resources with directed links between these resources. They, in essence, flow from one direction. Let me give you an example. So this is a very, very small portion of a graph with an anchoring FHIR patient resource, Ida Brown. You could see that she has a couple of observations that point to her: smoking status and blood pressure. She also has a link pointing out from her to her general practitioner. And that general practitioner has a link from themselves to the organization they belong to. These are all FHIR resources. But here's the challenge. When we try to represent all the information on Ida Brown in a real healthcare setting, we're going to find there's lots of conditions, diagnoses, observations, and encounters. So this graph gets very complex. If we want to summarize all this information easily, this is going to be very challenging because we got to pull in a lot of data. Additionally, it can be hard to search the graph for a portion of this information unless one is very familiar with FHIR search APIs and coding systems for FHIR terminology. So I wanted to show you what it looks like inside a FHIR repository. Here you're seeing a resource string coded in JSON. It has a few indices, as you can see on the left-hand side, but there are many rows of this data. So would we want to send this raw string to the LLM? Well, we can, and I've done that before, but it's not efficient and it's very token costly. Because FHIR is the data layer, we could use a structured knowledge graph. So we could get $everything can give us this longitudinal context on a patient, but then we could do things where we translate terminology codes. If we do that incorrectly, though, if code resolution is wrong, when an agent does a FHIR query, it's likely either to give no results or the wrong results will be returned. And we'll see this later. So we need to construct a bridge between retrieval and reasoning. We parse each resource type, group the content into clinically useful categories, normalize details such as units or status, and assemble a compact representation that's easier for the model to use. This domain-specific data model is optimized for LLM input. It reduces noise, lowers token cost, and usually improves accuracy. Well, this is an area that's very complex, and it's also an area where we find that otherwise promising systems, agentic systems, begin to struggle. So terminology, normalization, and code resolution. Users speak in free text, but FHIR queries require standardized codes. And the mapping from one to the other is often ambiguous and context dependent. Terminology resolution normalization is difficult because it's not just a lookup problem. It is a semantic resolution under uncertainty problem. The system has to interpret what the user meant, map that meaning into the right vocabulary, and do so in a way that preserves clinical intent. That is why this often becomes the intelligence bottleneck in an agentic FHIR system. There are three core reasons this is hard. First, free text is ambiguous. Second, multiple vocabularies exist for different kinds of concepts. Third, context changes meaning. If a user says diabetes, do they mean type 1, type 2, gestational diabetes, or a broader diabetic concept? The system has to decide, and that decision directly affects the correctness of the retrieval. Here is the terminology ecosystem our agent has to navigate. SNOMED CT is commonly used for conditions and clinical findings. LOINC is commonly used for observations and laboratory tests. RxNorm is commonly used for medications. The agent therefore needs to know both which vocabulary fits the concept and how to query it effectively. SNOMED CT or systemized nomenclature of medicine clinical terms, is a comprehensive concept-based clinical terminology used to represent diagnoses, findings, procedures, body structures, and more. It's designed as an ontology that's hierarchical. In FHIR, SNOMED CT is commonly used for coding conditions and clinical concepts, enabling precise and interoperable representation across systems. However, SNOMED CT contains on the order of 350,000 active concepts, with many more descriptions and relationships, making it the largest and most expressive of the major clinical terminologies. LOINC, or Logical Observation Identifiers, Names, and Codes, is the standard for identifying laboratory tests, clinical measurements, and observation. Each LOINC code represents a fully specified observation defined by attributes such as the component that is measured, the property, timing, the specimen that's used, the scale, and the method used for doing the analysis. It is widely used in FHIR for coding observation resources, especially for labs like glucose, creatinine, or hemoglobin A1C. LOINC enables consistent exchange across labs and health systems, even when local test names differ. Again, though, the LOINC database includes approximately 95 to 100,000 active terms, covering a broad and continually expanding range of clinical and lab observations. Finally, RxNorm, which is maintained by the U.S. National Library of Medicine, provides normalized names and identifiers for clinical drugs and drug delivery devices. It links together various drug vocabularies and supports interoperability between prescribing, dispensing, and medication history systems. RxNorm's concepts represents ingredients, strengths, and dose forms and include different term types. RxNorm is commonly used in FHIR in the medication and medication request resources. And again, it contains roughly 100,000 active concepts, including ingredients, clinical drugs, and branded products. But we need these vocabularies if we're going to have consistent medication representation across different health systems. So this is what real flow looks like. The user provides a clinical phrase, such as a type 2 diabetes mellitus. The terminology service may return several plausible candidates, and then the agent must choose one. The choice is not a detail. It determines what data gets retrieved, which patients are included, and what conclusions the systems can reasonably draw. Here's the practical consequence of code choice. If the agent chooses a concept that's too narrow, it may miss relevant patients. If it chooses a concept that's too broad, it may pull in the wrong cohort. So terminology selection is essentially a precision versus recall trade-off, but in a clinical context where the stakes are higher. The point here is that the selection step is where much of the intelligence lives. Retrieval itself may be straightforward once the code is chosen, but getting to the right code requires reasoning, context, and sometimes restraint. If the code is wrong, the FHIR query is wrong, and everything that follows is suspect. Production systems usually need heuristics rather than a single hard-coded rule. If the intent is vague, the system may prefer a broader concept or ask a clarifying question. If the context is specific, it can choose a narrower concept. It may also use patient context or task context to improve the decision. The important message is that the terminology resolution is part of the reasoning layer, not a side utility. A practical architecture uses a terminology service to generate the candidate concepts rather than hard coding mappings. The terminology service provides options. The agent then decides which option is best or decides that more clarification is needed. This is the clean division of responsibility. The service supplies candidates, the agent applies context and judgment. Context-aware resolution is what moves us beyond static mappings. So right off the bat, the agent must think through which terminology system do I query. If I have a glucose value, I'm thinking about observations. I'm going to use the Loink system. If it's diabetes, that sounds like a condition. I'm going to need SNOMED. And for metformin, well, that's a drug or a medication request. I'm going to need to use RxNorm. The demo I'm going to show you in part 2 of the workshop here uses an open source MCP server for terminology resolution. And I have the link here, and that's included, obviously, in the software I've provided you on the flash drives. In our case, we're using it primarily for searching for the correct code. The important point is that the terminology service exposes as a tool the agent can use to get different values and codes from these different code systems. One other point I want to make is that in building this prototype, I found out very recently that SNOMED International started to block Mr. Bissaloni's here terminology service for SNOMED. So I built a backup system that is fairly limited. I think in future sessions, we're going to have to build a more robust terminology service, but this terminology service works very, very well for both Loink and for RxNorm. So once the agent has selected the concept, it then has to close in on converting that concept into a form that FHIR search expects. And this usually means creating what we call a token in FHIR. A token consists of a system. So you see on the screen here, the system bar code. So the system here is SNOMED info/SCT, and then a code of 44054006. The agent has to basically create this FHIR token so that it can use it in building a query search string. So at this point, I'd like to connect the ideas we've covered and point forward to the demo-oriented part of the session. We've discussed the agents, FHIR, terminology, and retrieval. How we're going to put this together is we're going to create this summarizer in which all of these pieces are used. It's very practical. It's a reusable use case, but it's only one use case. I'm going to show you some other use cases as well. It starts with raw FHIR data and ends with a structured clinical summary that's human-friendly. So what we're trying to do is take that large, verbose, machine-oriented bundle that comes back from a FHIR search into a clinically legible and LLM-friendly narrative. The summarizer turns out to be a great use case for creating what's called a sub-agent. Instead of letting a general-purpose agent do everything, we create one specialized sub-agent to perform a narrow job: retrieve, parse, extract, and summarize. That narrower scope usually improves predictability, reliability, and debugging. The summarizer sub-agent retrieves patient data, extracts the key clinical features, reduces the size of the data, produces a structured representation, and then feeds that into the LLM. In other words, it's the bridge between raw FHIR and useful AI reasoning. And I'd emphasize this is not a general purpose agent. It is at the very defined goal, a limited tool set and constrained behavior. Even though the summarizer is specialized, it still follows the core agent loop. It plans within a narrow scope, calls its tools, processes its results, and continues until it reaches its goal. The difference is that the workflow is constrained enough to be more predictable and easier to validate. So the summarizer has 5 stages: retrieval, parsing, feature extraction, data reduction, and LLM reasoning. The first step is to retrieve the patient record, often using this tool, FHIR_everything, which under the hood does a $everything request of the FHIR repository. That response then comes back as a raw search set FHIR bundle and a very large longitudinal view of the patient. Once the bundle is retrieved, we could parse that raw JSON and turn it into more structured internal objects. We normalize the shape, group related data, and prepare it for feature extraction. At this stage, nothing especially magical is happening. This is just disciplined data engineering. Now we decide what matters clinically. We pull out active conditions, recent labs, medications, key encounters, allergies, and other high-value facts. Just as important, we ignore administrative noise. This stage largely determines what the LLM will be able to reason over later. After extraction, we compress the information further into a compact structure. The goal is not to lose clinical value. The goal is to reduce redundancy and noise so the model sees a small, relevant, token-efficient input. This is where the systems becomes both cheaper and more scalable. Now, this is what we need. We need to segue a little bit to token management and why it matters. Because ultimately, when you're using these models, at least in the near term, you're going to have to pay for them. Not for this workshop, but in the future, you'll have to pay based on the number of tokens. Those tokens are computed both on the input side, so how much are you sending over the wire to the model? If it's remote, like GPT 4.1 mini, how many tokens are you sending? And that includes your prompt too. And then how many tokens you get back. So you're going to pay based on the total token count. And that also, too, the more you send it, that's going to also influence the latency. So how long does it take to compute the output? So basically, I'm going to show you in the demos, you'll see that we could reduce the token size and reduce the cost of the system to be probably on the order of 20 cents per summary. So after we do that, only now we could hand that structured summary to the model. And at this stage, the model no longer has to search, filter, or infer structure from raw data. It could do what it's best at: interpretation, summarization, and explanation. And so this is another important design principle in this workshop. Use the model for reasoning, not for avoidable data wrangling. So what does the subagent actually accomplish? It identified the relevant resources, extracted the right fields, ignored the low value content, and produced concise output. So that's much more than formatting. It's a form of structured clinical reasoning over a constrained data set. I want to say a word about the system prompt. It's much more than a style instruction. It is where we define the operating model for the agent. In our implementation, the prompt is assembled in layers, starting with identity, then tool guidance, then security, developer instructions, user instructions, memory, FHIR-specific rules, and operational guidance. That means the prompt is acting as a policy surface, not just a personality surface. The practical value is that the prompt can force consistent behavior across terminology resolution, reverse chaining, sub-agent delegation, and output formatting. That matters because FHIR questions are often ambiguous in natural language, but the downstream operations must be precise. So I would just emphasize again that good prompt design should follow a layered architecture. Not all instructions belong at the same conceptual level. The identity tells the model what role is playing. Tool guidance tells it how to think about available actions. Security and project instructions constrain behavior. And FHIR-specific rules are inserted near the end so they are close to the final decoding context. So here's how we can turn a prompt into a safe reasoning path. The sequence in our system prompt encodes a mandatory order of operations. First, the agent must classify the clinical domain. It must use MCP terminology tools to resolve the natural language term into a standard code, and then it checks whether the answer may already exist in code examples or cache patterns. It uses reverse chaining when necessary, so the FHIR query is constrained correctly. Only after that is it allowed to call FHIR search. Good prompt design can reduce hallucination and inefficiency. Instead of letting the model improvise a retrieval strategy, the prompt gives it a disciplined path. And I'm not going to go too deep into this, but basically your main agent shouldn't try to do everything. This is where, by good design, you could create sub-agents, such as the sub-agent FHIR summarizer, which we'll see more of. And that prompt should have its own orchestration and skills to do what it needs to do correctly. So a good FHIR system prompt is explicit, layered, and testable. It tells the agent how to route work, when it should use terminology resolution, and when it must use sub-agents. So why this is essential is because some of the biggest failures in healthcare agents come from shortcuts, going straight from free text to retrieval, confusing free text with coded meaning, or trying to do every task in one large context window. Production-grade prompt design ideas include layering, recency-aware rule placement, deterministic tool order, and delegation. I'm going to cut this short. We could talk a little bit about FHIR skills, and the sub-agent is a great place to program skills. But in the interest of time, I want to make sure that we do get a break and have the ability to answer some questions. But before we go to part two, I want to emphasize again, we're going to see in the second part of the workshop the demo application. We're going to actually use it interactively. It is an open learning tool built in Python. It's designed to run in a very familiar development environment that you could extend easily on your own with additional tools or sub-agents. It's totally open source. It's education. It's not production ready. So this is not in the product. This is a fully open source code base that you could use. And with that, we could take a break and I can answer some questions. Do we have any questions? And can we get somebody to use the mic? Can you go to the mic? Is the mic on?
I was just wondering about ICD-9, ICD-10, and CPT. Do you have them included in your terminology system?
The open source MCP server we used does have those included, but we did not use them, not for this demo. So if you wanted to use and extend out to ICD and other terminologies, there are terminology servers for these. But I think you got to look at licensing restrictions too, a little bit with ICD and some of these other term systems.
Yeah, but do you find these things commonly in FHIR resources?
No, not as much. I mean, the three biggies are really SNOMED, LOINC, and RxNorm. Those are the big ones. But I'm sure people use other systems too.
Will you pull back up the slide that had the components of your prompt? And I just want to speak a little bit about the security component of that.
Components.
The concept of removing that from the actual prompt and making it a deterministic code, and how much of that could be deterministic versus, generative. Yeah, that's great. So the security and policy piece of this. So there's a real challenge with generative AI to actually agree to the prompt that you actually put into it, that it actually performs and does that work. And how much of this could be actually extracted from the prompt component of this and framed within a harness that would allow it to have the security policies, the things of that nature, that it would not allow it to function outside of that because you've got hard-coded rules written into this.
Right. And I'm going to show you that in the second half, where I'm going to use some security policies that are outside of the agent that essentially intervene when we try to do a FHIR update operation. Good. You're going to see it's going to know that the agents has to call the security layer to get approval for that. And we'll get to see that actually in the demo.
Thank you.
Hi, kind of a similar question. When we talk about putting those guardrails in, one of the things that we've run into is our general purpose agent being overall too helpful and trying to end run our invocations of subagents, particularly if it's experienced multiple failures. I couldn't access, like the subagent didn't return this call from the MCP, so I read the MCP logs and found the stale resource from an hour ago and moved forward with that. Do you have any guidance or strategy on how you sort of create that abstraction layer to try and corral a really helpful, overly helpful agent?
Well, this is an interesting, good question about, how do we put more guardrails in? And this is where I'd say this. These systems are not going to replace engineers in the near future, to the best of my knowledge, because you have to do a lot of experimentation in terms of locking these systems down, both in terms of the prompts, what tools they could use, and creating better specificity in the answers. And, human in the loops are going to be needed for very sensitive operations. But yeah, we're going to need engineers to help with that problem. And we're never going to get a perfect system. I don't think it's achievable. We'll just do our best.
Well, as an engineer, I like that answer.
Okay. Well, so do I.
Yeah, I have a question. Does this involve an OAuth workflow, like the scope parsing to the FHIR call?
Does it involve what workflow?
OAuth 2.0.
Oh, no. For this demo, I thought OAuth would just add needless complexity. A lot of the people in the audience probably haven't even used OAuth. But, the good news is if you take my FHIR course, we do teach OAuth too, and can show you how to use OAuth to do all these kinds of
I'm
things.
just kind of wondering like for instance, if I work with German enterprise, right? The first thing they would ask is how do you pass the OAuth token into,
well, you got to get the token, right? And then you can pass it in. This is just an engineering problem. We could absolutely build an agentic system that uses OAuth inside of its tools. It's just going to be more complex, but it's definitely doable.
Thank you.
Maybe similar to the earlier question, FHIR has limited expressibility or expressiveness for the universe of even just nouns. Do you have any advice for addressing the broader universe of the problem space besides just what FHIR can express?
Well, yeah, I mean, there's no question that if you look at what's inside a electronic medical record, FHIR is just a subset, right? I mean, there are many more tables, many more data sources. And so the principles that I'm talking about apply, but FHIR is just one very good way in which we could have a fairly good standardized data layer, but it may not serve the use case that you had in mind, because if the data isn't in the FHIR repository, it's going to be won't help you. So you would just build an agentic system, but look at non-FHIR sources of data, which could easily be done. All right. We could take a little break. I think we should be back by, 4:35? How does that sound? Well, let's start up part 2, because it's probably a more interesting part, and we want to have a little time at the end for questions. We've covered kind of a lot of concepts, a lot of theory. We covered architecture. But what I want to do in the second half is really just show you how this works in action. So show you these tools, show you a little bit about the implementation details. So we're going to focus on execution in this second half. We're going to walk through how the agent retrieves data from FHIR, how terminology feeds into search, how a bundle becomes a compact summary, and what safety and production concerns appear when you move from the demo area to deployment. Everything we've discussed so far depends on retrieving the right clinical data. So this section is about how the agent's tool set, how the agent chooses among these tools, and how those choices map to concrete FHIR operations. So this is where the workshop's going to feel a little bit more tangible, I hope. So here are the tools. You're looking at the tools that are the agent's API surface. Some are very narrow and direct, like FHIR_read. Some are more flexible, like FHIR_search. Some are broad, like FHIR_everything, which uses a $everything operation under the hood. And some are composite abstractions, like the summarizer. The point is that the agent is not improvising against the repository. It's operating through this defined tool layer that you see on the screen. So let's take a look. This is the simplest retrieval pattern. So here I'm saying, if the patient ID is already known, you know it for some reason, the agent doesn't need to do much reasoning at all. It simply chooses the direct read tool and fetches the resource. So let's see how this, in a very simple demo, let's see how little reasoning we could get by with and have an agent really return still some good results. I'm going to combine that though, with this next operation, FHIR search, to show you some basic queries. So here I would like to show you how you could search for patients with various criteria, again using the FHIR API. So it needs more than direct lookup to do this. You may ask for patients that meet a certain criteria, like women named Smith, and the agent needs to translate that into natural language intent, into formal FHIR search operations. So let's take a look at that. Move over to the demo screen here. I hope everybody can see that. I've now started the program. I'm running it in the, so you're seeing the major agentic loop. And the first thing you see is the model and what working directory, that's CWD, and a bunch of commands. But one thing you should do if you're playing around with this software, I would say use the /help command to get some information about what help things are available. So you could see things like you could clear the conversation history, you could check out the configuration, you could change the model, you could get stats about the current session. We're in a session right now. And we can look at the tools and MCP servers that are being used. So why don't we just do a little bit of a tour of that? I think the most important thing I found helpful is the /config prompt, where we're just getting back which model we're using here, GPT 4.1 mini, and how we've set this up. So we have approval on request. Here's our working directory. Here's the maximum number of times we'll allow the agent to go in a loop, 100, which is probably far too many, actually. And most importantly, here's our base FHIR URL. So this is telling the system, hey, I need this base URL to reach the FHIR server that I'm interested in here, and here's the FHIR schema. That base FHIR URL is basically configured in this config.toml file. So you could change that, and you could also change what tools are allowed by the agent, what models allowed, etc. Okay, so there's a lot you could do. It's fairly easy to customize. Let's take a look at also, we could find out what MCP servers are connected to this system. And we only have 2. Notice we have a file system with 14 tools. We're not even using any of those tools. So this would be, like things like your bash command or grep. Those are tools that a agentic system could use. We're not using it for any of this demo. But we are using a medical terminologies MCP server that has 27 tools in it. But we're only using a very small subset of those tools. So let's take a look at what we are actually using. Well, I've mentioned we're not going to be reading and writing files and things like that. But we are going to be doing things like FHIR_search, FHIR_read and update, FHIR_everything, and the FHIR and the subagent FHIR summarizer. We're going to use all of those tools. Also, medical terminologies. We need LINQ search, RX norm search, and SNOMED search. And as I mentioned, SNOMED search is being blocked, but I have a backup in the system that will look at some common SNOMED terms. So let's just ask it a question and see what results come back. Get me 10 patients from the FHIR repository. This is kind of the simplest level of question you could ask. All right, so the first thing it's doing is it's creating this bundle And it is going to create a summary here. And you could see, okay, it's returning 10 patients, but let's trace back. How did it even get to that point? What did it do to be able to get to the point where it can return anything? Well, it had to call a tool, and you could see here's a tool call to FHIR search. It had to know that it was looking for patient resources, and it said, okay, max results 10. As you could see in this next layer, the output layer, I have it programmed to show exactly what the FHIR query it developed is. So it took the base FHIR URL and then concatenated this query string _count equals 10. That didn't limit it to 10, by the way. It just meant it limits it to how much is in one page. There are 115 entries that were returned. False reverse chaining was not needed for this. And then you're seeing the bundle. You're seeing what's called a search set bundle come back. And so this is what FHIR is, what it looks like when you give a correct FHIR API query. So we'd like to take a look, and I truncate the bundle at the end here because it's so large. So we see we got these, we have these 10 patients and we have their FHIR IDs. Okay, so why don't we ask it to please return the FHIR patient resource for, let's say Stuart Cronin. Now his FHIR ID is 8. Let's see if the system reasons about that correctly. And it does. Okay, so here we're getting back again the resource string for this patient in FHIR. It's not particularly, you'd say, well, it's not really human readable per se, but the point is FHIR is just an API that's used by applications. So here we see it correctly called the FHIR _read operation. It got back patient 8. This 200 means this response was accepted by the FHIR server, and we had no errors in the response. So let's try something more sophisticated in FHIR search. How about is there any patient named Larson in the FHIR repository? Yeah, and there's a Stuart Larson. Okay, so here it's having to do a search. So how did it do that search? It had to make a FHIR call, but it had to construct this query string. So it had to figure out that name equals Larson. And in FHIR, when you're doing a search, there's only certain search parameters that are allowed. Let's maybe make it do something that's a little bit more refined, but the same kind of idea. How about getting back any patient with a family name of Larson, who is also a male. Okay, so how did it reason through this query? So here it had to construct a Boolean query string. So it said, okay, family equals Larson. That is, by the way, I happen to know that family is a valid search parameter on patients. And the gender equals male. So it's able then to get the search set bundle back. There's only one person in this bundle. I mean, we could ask it a more complex question. Let's say, how many patients are in the FHIR repository that are women? And it comes up with 62. So how did it know to do that? Well, here it's going to get a patient. It knows it's supposed to get a max result of 1, gender equal female. It sees there's 62 entries, but now this is not actually a valid query. Well, it is a valid query in FHIR, it is. But there is even a more sophisticated query it could have used. It could have done summary count, it could have been summary equals underscore count, and it didn't do that. And, that's an engineering problem. We could fix that, but I'm just trying to show you that this is not some kind of magic machine. If it doesn't know about some of these rules, it will not use the most efficient methods. Let's go back into our slides here. So that's a basic query. Let's look now at a tough problem, this terminology resolution problem. So we want to resolve patients, or we want to develop cohorts in the FHIR repository. And basically what that means is we need to find people with certain conditions. But conditions in this data set, and this is a synthetic data set, are all coded according to Snowman. So we have to resolve these codes if we're going to get back these patients. So what happens if we don't specify exactly the kind of diabetes? Well, I could tell you, obviously, we're not going to get the correct code because we won't have it in. There are no patients in this FHIR repository that are coded directly according to with the general diabetes. That doesn't exist. So under the hood, though, in addition to terminology resolution, we got to get the correct system and code, and we have to do reverse chaining in this case if we're going to get back all those patients. So as I mentioned, here's what token search is in FHIR. You have to have a system and code. So the system, we need the LLM or the AI agent to correctly figure out what system to use and then pick what code to use. And if it does those two correctly, it has a shot at being able to get back the correct resources. Here is an example where the system had to figure out, using Loink, all the observations for glucose. And we could show that in the demo here. And here's what we mean by reverse chaining. We want to find all those patients. So we're searching for patient resource, but they have to have a certain condition. And this is where, if you aren't familiar with the FHIR syntax, this may look confusing. I mean, it is a syntactic pattern that's valid, but it may be a little bit obscure. So we have to get a condition that references the patient. We need to do what's called inverse traversal. And, here's some examples of that. So the agent, under these conditions, we got to extract a concept. We got to resolve it via MCP because that's where our terminology services are. We have to do a _has type of query, and we need the agent to construct that. And then we have to execute the search and hopefully get a result back. So let's try that out. Let's try that out with a couple different conditions. All right, let's try to go with find all patients in the FHIR repository with type 2 diabetes. Now, it found these 6 patients, and it produced a bundle. It didn't summarize. It's interesting. In this case, it didn't summarize. I didn't say it had to do that. So it just gave me back the raw bundle. But let's take a look at a couple things here. First, it had to call that medical terminology SNOMED search. And as I mentioned to you, that's blocked. So the system had to retry. First of all, it got a failure response. Notice we got a 410 error. That's from SNOMED blocking our call through that MCP tool. So it then used the local SNOMED fallback that I programmed into it because this MCP SNOMED API was not available. That is part of essentially engineering a more robust system. But once that's done, once it was able to use that local repository, it was able to resolve the token correctly. Notice this, it used the SNOMED system, and it's basically asking, it knew the clinical domain was conditioned. And so it returned the bundle, and there are a total of 6 exact patients. So it was able to do this correctly. Let's try something else. How about find all patients with allergy to peanuts. Oh, okay. So it said there are 4 patients, and it gave me, again, the bundle. Let's say, summarize these patients' name and FHIR ID. Okay, so pretty simple. Should have done that right off the bat. But again, if I wanted that and I'm not giving it much in the way of context clues, then I need to build that into a better prompt for it to be able to do that in any kind of reliable way. Okay, so now we want to look at getting some, we've looked at targeted retrieval. I want to expand to full patient retrieval with dollar everything. And this is useful when the question is a broader clinical context rather than these really narrow questions we're asking. The trade-off is that the output can be very large, which makes downstream processing essential. Okay, so let's see that before we do the FHIR update operation. I'll show you. So how about we do this? We say, show me a clinical summary on patient 1. So now it's got to pull all that data. So it's it's calling the sub-agent FHIR summarizer, and it has the goal. The first step, it's got to do that $everything request under the hood. But then after that, it's got to extract from the FHIR bundle that's returned, and that could be quite a large bundle. So that's going to take, there is going to be some latency with that. The final thing it has to do is it has to format the output in the way we've crafted our sub-agent prompt. So we've instructed it that we want the output of that summary to look in a particular way. So let's see what it comes back with here. Okay. And you could see, let's take a look at this. Here's the result of the sub-agent FHIR summarizer. It completed the sub-agent task, so it terminated. And when it terminated, it returned to what? To the main agent. It used just this one tool, FHIR_everything, but under the hood, FHIR_everything used this bundle extractor to extract things like the name, the date of birth, the gender, and the active conditions, because that's what we wanted. It got the medications, recent encounters, recent observations, allergies, and notable clinical findings. So it did a pretty good job here. The nice thing is once you get data formatted like this, then you could do other queries. But let's see, one of the things I told you about was data reduction. So let's take a look at our stats. Where are we in terms of token count using this model? And so far, we've used in this session, so that includes all those other little demos, a total of 539,597 tokens. So we're doing pretty good. We're not definitely at $1 yet. We're still under $1 in terms of our prompt tokens. Our completion tokens are still relatively low. So this is why you do want to do that kind of data reduction. But it does, one of the things you could do when you have the context, of course, then you could ask it questions about the specific patient you retrieve. So I could say, for this patient, what treatments or preventative measures should the clinician consider? Okay, continued anticonvulsant therapy, regular neurologic follow-up, safety counseling. Excellent. So these are all things. I'm a neurologist, not active any longer. Long ago, gave up my practice. But these are reasonable actions to take in somebody who has epilepsy. All right, let's go back. So $everything gives us a comprehensive starting point. How about update operations? Okay, so this is where we've been doing up to now just read-only examples. And so now we're marking a transition to write operations. By that I mean we're going to want to update things, and this is where we need to have some guardrails. The architecture must change. We need things that will ask us for approval, We want traceability in that. We want strong controls because it's much more important when the system is doing these in real clinical patients, not this synthetic patients. We need to be observing what is happening under the hood. It's not acceptable to just let the agent go do its thing. So let's take a look at that. I'm going to ask it to find 10 medication requests. FHIR resources. Let's just take a look when we get back. Okay, so we see we got 10 medication requests, and we see what patient ID they have, but we don't know their medication request IDs. Let me ask it that. Okay, so it's saying that the medication ID for the first listing, Aaron 28-day pack, is 53. Okay, so notice what it said here, though, is that this status of this is stopped. So what if I wanted to do the following? I'd say, all right, for medication request 53, change the status from stopped to active. Okay, so what that is triggering in the system, and this is, again, this guardrails problem or guardrails issue. It knows it needs to use a FHIR update operation. But per policy, we've set FHIR update operations to require approval. And so it comes back with approval required. It has not done this update operation yet. And it's waiting for me to say yay or nay to this. And so let's go ahead. We'll say yes, because it's all synthetic data. But in many other circumstances, you may not want that. So if we say yes, notice we do have a FHIR update operation, and we've changed the status of this. So that's an example of the engineering around the agent, where if it's doing a critical operation, in this case, in anything in FHIR that deals with rights or updates, you're going to want to get approval almost invariably, unless it's something extremely routine. So obviously, why it's required? Well, write operation, change the stakes. If you write this into the FHIR repository, this is affecting care decisions and becomes part of the legal medical record for this patient. Now, synthetic patients, we don't have to worry about their legal medical record, but in other cases, it would be. So this is not just a technical problem. It's more of a governance and patient safety issue. So you need the read and write operations should never be treated as equivalent in FHIR. Let me make this more concrete. If we're updating medication dosage, changing a diagnosis, adding allergy information, deleting data. These are all very consequential actions. So the point is that agents should never support these workflows without having a human in the loop. They need explicit approval model. And the way to do this is creating policies that lie outside the agent, but the agent is tied to those policies because it knows that it has to invoke those policies for certain tool operations. So here's approval policy defines when approval is required, who could give it, and what must be logged. And that includes trigger conditions, the affected resource types, the operation type, the required approval role, and the audit record. So this is the governance layer that separates it from is separate from the model itself because it is a safe architectural pattern. So this is full human in the loop. The agent proposes a right, the policy layer evaluates it, a request for approval is generated if needed, the human approves or rejects it. All right, so we're connecting retrieval, terminology, and transformation in the complete workflow. So once we have the data, how do we make it useful? So this is the bridge from large bundles to user-facing summaries. The overall flow is we retrieve, we structure, and we summarize. And the clinical or the critical middle step is often the part people skip because they think we could just go from raw retrieval to summaries. But that doesn't necessarily make the data usable or consistent. So the bridge is structured reduction. So this is kind of what the prompt looks like for the FHIR summarizer. It's a defined subagent. It's not a loose prompt. It has a clear goal, a constrained tool set, a defined scope, and a very predictable return path to the main agent. So it's much closer to controlled execution than free-form chat. So let's see step one. Step one is telling the summarizer how to read the bundle. We explicitly instruct it to focus on clinically relevant resources and to ignore administrative noise unless it matters. This is important because summarization often improves from knowing what to ignore than from knowing what to include. So we're having it focus on patient, condition, observation, medication request. Step two is feature extraction. We define the categories of information we want the summarizer to pull out. Demographics, active conditions, medications, encounters, observations, and allergies. And we could do this, by the way, using both Python and FHIRPath. This is effectively schema design inside the prompt. We're telling the model what the structured output should contain. Step three is the output structure. We're going to specify the sections and the format of the summary so the outputs remain consistent. And that consistency, I think, does matter for readability, for evaluation, and for downstream use. Good prompts define both intent and shape. And then there's the anti-hallucination rules. We explicitly tell the model not to invent data, to summarize only what is present, to say not available when information is missing, and to say concise and clinically relevant. Production introduces a different set of questions. Latency, token cost, repetitive terminology lookups, compliance, and observability. At this point, the system's no longer just an LLM demo. It's a distributed application with an LLM in the loop. And this is the right mental model for deployment. So let's take one more look at how we summarize a patient. We've seen it a few times. I'll do another query. Okay, so it's making a call to create this. That's the goal. Clinical summary, patient ID 6. And again, it's pulling back that bundle and structuring it so that it could be used by the LLM. And then the LLM has to follow the prompt that we've provided to format the output in the way we described. And again, this could take a little bit of time just because of the number of resources that any patient might have. And that should be kept in mind too when you're building systems like this. In part, it may be wise even to do caching of some of these summaries if that's what your goal is to make them available in kind of like near real time. So this took a little bit of time, but you could see it found the active conditions: hypertension, prediabetes, anemia, miscarriage. Really quite a lot of data in this. Recent encounters, medications, active conditions. So this is exactly what we want this tool to do, but it can take quite a bit of time to get all that done. So just a couple last things from me, and then I'll let you go here. I wanted to just talk a little bit about design patterns, safety, and production concerns. We've already covered some of it, but the most important thing is to emphasize that the LLM should be your reasoning layer. The tools are handling execution. So FHIR retrieval, terminology resolution, and summarization should each be represented with clear capabilities. Better tools usually mean simpler prompts and more reliable systems. Sub-agents help control complexity. Instead of having just one agent trying to hold the entire problem in context, we should create specialized reasoning units, such as a summarizer, a code resolver, or a cohort builder. That decomposition usually improves reuse, reduces hallucinations, makes the system easier to test. Least privilege is one of the strongest safety defaults you could have. Agents should only begin with read-only access and gain additional capabilities after you've done a lot of testing and the workflow justifies it. That means read operations could be broadly allowed, while write and delete operations should be tightly controlled, especially in FHIR. Keep in mind that even when an LLM output looks plausible, it may still be wrong. Structured validation that our FHIR server provides does a first post-generation safety check, you could think of it. But even a syntactically valid FHIR query could be in error because maybe it's using the wrong codes, for example. That's why human in the loops are important. Observability is not optional in healthcare AI. At a minimum, you want to log terminology resolutions, FHIR queries, selected codes, and approval decisions. If the system produces a questionable result, those logs are what you let it will help you reconstruct what happened. They're essential for debugging, auditing, and trust. A message that I've already mentioned is that production systems will fail. Terminology may be ambiguous. Fire servers may time out. Results may be empty. And data may be inconsistent. In fact, 1 week before doing this workshop, I mentioned the SNOMED International Code Browser went offline. So having a backup plan for that is very much a part of good engineering design. And it'll allow the system to fail gracefully when it reaches these failures. And the system, remember, it has an agentic loop, so it'll do retries or fallback queries if it's given instructions on how to do that. There's a lot that you could do if you want to learn more and go deeper. There are additional sessions and Python and also a Python-based FHIR course that InterSystems offers. I want to close with one strong takeaway. Agentic AI plus FHIR is not about replacing healthcare systems. It's about making structured healthcare data and workflows more usable through better orchestration and reasoning. So, what more can you do if you are interested in this area? Well, first, there's a working group within the FHIR community called AI Transparency on FHIR. They're constructing a FHIR implementation guide to provide guidance for the usage of AI influencing FHIR resources. That may be a group that you may want to work with. HL7 groups are a great way to learn more about FHIR, especially influencing the design of the standard going forward. The other thing you might want to check out and is in this program is the InterSystems AI Hub that's coming. It's not quite here. It's in the EAP form. It's coming to IRIS and IRIS for Health. This will help you build AI systems and agentic workflows more quickly and safely, and it offers a lot of different experiences, including working with ObjectScript, working with the model context protocol that I showed you today, and also it interfaces with hugely popular frameworks like LangChain in Python or LangChain for J in Java. There's a lot of really good sessions I urge you to check out. Tomorrow, there's going to be a thing called Firestorm, a Firestore in the AI Accelerator. But we have a lot of interesting AI agent talks this week, transforming a chatbot into an AI agent using InterSystems IRIS for Health, multi-agent work orchestration for enterprise workflows, agentic engineering that's going to be live on stage, AI and interoperability, building AI apps and agentic workflows faster with AI Hub, that's that new experimental EAP feature. So check those things out. And lastly, if you're interested in learning more about FHIR because you feel like, well, I could use a lot more FHIR understanding, we are building, and I'm in charge of, a course on FHIR. This is 45 hours of material. It's recorded, but we have live sessions weekly, and we cover basic or introductory, intermediate, and advanced FHIR. And we have 2 cohorts going on right now. We'll have another one at the end of the summer. So if you're interested in this, check out this program. We have a dedicated website for learning FHIR. You could start with the basics and then move your knowledge up. And lots of good recordings and quizzes, question discussion sessions. Participants post questions and we answer them, so all the students can get advantage of that. So that covers a lot. At this point, I'm happy to take any of your questions. Are there any questions? And if you do, can you go to the microphone? Well, if there's no questions, be sure to copy that stuff onto your laptop. You can play with it. I think that's a great way to learn too. And all the source code is there too. So you have all the code. You can modify it. You can do anything you want with it. All right. Well, thank you very much.